Thank you for the introduction. So, I will continue this historical survey of the classical algébrisation theorems before I go to SGA2 properly. So, as I explained, so we have the theorem of Chow that I discussed, and another classical algébrisation result is the theorem of Poincaré, Lefschetz, Hodge, which was given later on a new proof by Grauert and Spencer. In 1953, which asserts that if we take X, let's say, smooth and projective, any complex, any analytic line bundle over X is algebraic. Okay, so as I explained, concretely speaking, it means that it has some meromorphic section. So it's defined by a divisor, and this divisor by two theorem is algebraic. And of course, as you know, slightly later on, slightly after the proof by Grothendieck and Spencer in 1956, all these theorems have been subsumed in the work of Serre, in the so-called Gaga theorem, géométrie analytique, géométrie algébrique. So the context is the following one. If you take any complex algebraic variety, let's say separated scheme of finite type over C. Okay, so it's defined by some space X or X, ring-out space. To any such thing, you may attach some complex analytic space. By some analytification functor. So more generally, if you have F, some current algebraic sheaf, current sheaf, and OX, it defines some current analytic sheaf. And Xn. So here, the associated space is a space of complex points with analytic topology equipped with some natural sheaf of analytic functions. So namely the functions that may be defined locally as analytic functions of the functions, of the algebraic functions. And the theorem of Serre may be split in two parts. There are two parts in the proof that are actually of quite different level of difficulty technically. The first part is a kind of comparison theorem. Okay, you start. Okay, in Serre's theorem, you work over X. Let's say complex projective variety, complex projective scheme. It's a projective scheme over C. So the comparison theorem asserts that for any algebraic, well, any current sheaf on X, so it's an algebraic current sheaf. To any such current sheaf, you may consider the cohomology group of this current sheaf. And by analytification, they are mapped to the, let's say, analytic cohomology group associated to the analytic current sheaf. So you have this analytification maps. For instance, at the level of H0, if you have a regular section of F defines an analytic section of F. And the comparison theorems assert that these analytification maps are isomorphisms. And the second part of the theorem is a kind of existence theorem. So it's 1, 2, which asserts that any current analytic sheaf on Xn is isomorphic to some Fn for, well, to Fn for some F current on X. So you get, well, a consequence of these two parts is that the analytification functor from current sheaf on X to analytic current sheaf on Xn is an equivalence of category. This isomorphism, this F is because of the first part of Gaga applied to morphism, to the sheaf of morphism between sheaves. You get that F is a unike up to a unike isomorphism. Okay. So of course, these theorems are extremely strong and contains a lot of previous results as special cases. For instance, it contains, of course, a Chau's theorem. So let me give some comments. It contains Chau's theorem. Because, of course, you work with X is Pn. And if you are given Y, a closed analytic subset, in Pn of C, you take as F, you take the current sheaf O of Yn, current sheaf on Pn, analytic current sheaf on Pn. And according to the second part of Gaga, to the existence theorem, it's the form some F n for F current on Pn C, and it proves that X is the support of F, which is an algebraic current sheaf. So Y is algebraic. Yes, but well, it's. But then I have to algebraize also the morphism. I have to know that it will be an ideal, so I will have to algebraize a map to ON. It's the same proof. It's the same argument. So I have to say the same. And of course, clearly, it contains Poincaré, Lefschetz, Hodge, Grauert, Spencer. By take a line bundle is a analytic line bundle is a very special instance of an analytic current sheaf. And of course, it implies, for instance, many things. For instance, the unicity of the structure of algebraic varieties on projective analytic manifolds, and so on. And you have many concrete applications. For instance, the kind of very standard application is that if you take X, a complex projective variety, it's connected. You may look at finite et al. Cover finite et al. Morphisms from a projective variety x tilde to x. And of course, using Chow, you get that the subjects are in one-to-one correspondence with their analytic counterparts. U1. So it's like, okay, finite and ramified covering. Of analytic spaces. So here, I suppose X is reduced. And of course, it's clearly the things are obviously in one-to-one correspondence with the finite topological coverings. Well, topological coverings of Xn of finite degree. And of course, well, to do this, you have the map is an identification map. And let's say this construction is injective because if you have an isomorphism between two things that come from algebraic data, you apply Chow to some graph and you get that this correspondence is algebraic. And this functor is essentially surjective. If you are given such an object here, you may encode it by a current sheaf of algebras on Xn by taking the direct on O of X tilde n. So you algebraize it as a sheaf, then you algebraize it as an algebra. So it will define some finite analytic space over Xn. On this finite analytic space, you can very easily check that it is ramified by taking any kind of characterization of etalness in terms of discriminant, for instance. So, okay, it's a very standard thing. And of course, this is quite simple, but concretely speaking, it means exactly that this one-to-one correspondence corresponds to the fact that the algebraic fundamental group defined by classifying this objects is a profinite completion of the analytic fundamental group. So establishes that P1, let's say algebraic of X is canonically isomorphic with a profinite completion. Of the analytic pi 1. Okay. Okay. Now I would like to say a few words about the proofs of the theorems of Gaga and, or Grauert and Spencer. So, about the proof of Gaga. Okay, so first of all, as any projective scheme may be embedded in projective space, some kind of stupid reduction shows you that it's enough to prove it, to prove the statement when X is Pn. Actually, there is a slightly stronger form of Gaga, which holds for any proper scheme over C. And I suppose it's also true for any proper algebraic space over C, but I don't know where it's done properly in the algebraic space case. Okay, anyhow, but let's do it. And actually, there is a very serious level. Well, the two parts, the proof of the two parts are rather different. The first part doesn't require any serious knowledge of complex analysis. Actually, you make the proof of one. The idea of the proof is that to do some kind of dévissage of the current sheaf F, and basically you reduce the proof of the isomorphism of these maps to the case which is one of the tautological line bundle O of n. And in that case, you conclude by direct computation. Very easy to compute. Actually, to complete this proof, you don't even need to know what a current analytic sheaf is. For instance, you don't need to know, well, it's not completely, because of course, coherence in a pure algebraic geometry is something, well, on Noetherian scheme is something quite cheap, but coherence in analytic geometry is rather subtle, and the coherence of the structural sheaf is this deep theorem of Oka, and actually to prove one, you don't even need to know the theorem of Oka about the coherence of all of the analytic functions. And the proof of two of the existence part maybe today will be the most important thing to get some idea of. Actually, the proof of two is very much inspired by the proof of the new proof by Grauert and Spencer of the old theorem of Lefschetz. So it's inspired. By Grauert and Spencer. And let me explain the principle of this proof. So here's the main idea of the proof of Grauert and Spencer. So, Grauert and Spencer's work over some smooth projective subvariety in Pn of C. And they are given some analytic line bundle L over X. And they want to prove that it is algebraic. So the proof of Cohérents and Spencer works by induction on the dimension of x. For instance, a main non-trivial case, say, is when x is a surface, because basically you know this is true, that an analytic line bundle over a curve is algebraic, for instance. Curves have been created by God and the surfaces by the devil, and the proof of Gauss-Spencer is a way to tame the devil. But of course, you could start with a curve and reduce to a point. But think of x, a surface, and so the idea is to consider some auxiliary hyperplane section, smooth hyperplane section. Of x. Okay. So you assume that L restricted to Y is algebraic. So to prove that L is algebraic over X, Cohérents-Spencer works in the following way. So you introduce S0, a section of O of 1 over X, such that Y is defined by the vanishing of S0. Okay. And now you have the following exact sequence of sheaves, of analytic sheaves over X. The multiplication by 0 send OX minus 1 to OX, and the quotient is O of Y. Okay, so this, you write at the sheaf theoretic level that Y is a hyperplane section defined by 0. Okay, now you may twist this short exact sequence by any line bundle. You will still get a short exact sequence between a line bundle is locally free. So you can do that by L tensor On for any positive integer n. So in this way, you get the following short exact sequence: L tensor O x n minus 1 is 0. And you get the restriction so this and that are line bundle over X, and this current sheaf is supported by Y on the line bundle over Y. Sorry? N. Okay. Thank you. Okay, so you get that. And now you consider the long exact cohomology sequence associated to the short exact sequence.
Sorry, in the analytic category, this is in the analytic category.
Here we are in the analytic category.
So it's OXN.
Oh yes, I should might put an everywhere. Yeah, right. Thank you. Okay. And now you consider the associated long exact sequence of cohomology. Well, you consider only H0 and H1 groups. Okay. H0, H1. Okay. And now come really the magic of the proof. If you look at this very carefully, when you use a few basic things, you are basically done. So you will use three things. The first thing, it's H1. It's something that initially, that is basically something of analytic nature, is that these H1 groups here are finite dimensional. Analytic. Line bundle M over X. So, in the paper on Grauert and Spencer, it's proved by using some kind of elliptic analysis. H1 groups are Dolbeault cohomology groups, and you can identify this H1 group with, let's say, harmonic forms, kernel of D bar star D bar for the D bar twisted by L. And this is an elliptic operator, so it's kernel, and this cohomology group is finite dimensional. So there's some kind of elliptic analytic result. Okay. You know that. And you also know, for instance, if you work with curve on the surface, you certainly know that this analytic H1 group on the curve vanishes when n is large. It's easy. You know something on Y. And you also know that, of course, L, this space is very large. So okay? On the curve, a line bundle of large degree is generated by its sections, for instance. Okay. And now, if you look at this carefully, there is a very nice purely algebraic trick. Using this, you see that this implies that for n large enough, this map is onto. Is onto. So once you know that this map is onto, you know, for instance, that this space is non-zero. So you have a global non-zero regular section of L times On. So you have a meromorphic section of L. So L is defined by some analytic divisor. And by Chow, Grauert and Spencer conclude the fact that L is algebraic. So let me explain this very simple thing. So it's a very simple argument, very nice and very cute. So it goes as follows. If n is large enough, this is 0. So replace this by 0. So it means that for n large enough, these maps are onto. But now look, these are finite dimensional complex vector spaces by this finiteness assertion. So now look at the sequence of the complex dimensions of the spaces. It's a sequence of integers that doesn't increase. So at some point, it has to be stationary. So the dimension, equal dimension, for n very large. So, but if this map is onto, and these dimensions are equal, this map is an isomorphism. And if this map is an isomorphism, this map is 0. And if this map is 0, this one is onto. Okay? Very, very easy. But in a sense, it's a very strange argument. It's a very strange argument in the sense that it is completely at the opposite side of the world as what was discussed by George in his previous talk. It's difficult to make an argument that is less effective. It's completely ineffective. You use at some point that a non-increasing sequence of non-negative integer has to be constant at some point, but of course the proof doesn't tell you anything about that, about the level where it will occur. Okay. Okay. So the point, this very cute purely algebraic argument occurs in the paper of Grauert and Spencer, and also plays a key role in the proof of Serre of Gaga. Actually, Serre had a footnote in his Gaga paper telling, OK, on reconnaît ici l'argument essentiel du papier de Grauert et Spencer. Blablabla. So it's completely OK. OK. So, and basically, the idea of Serre is to work by induction on n, when you work over Pn, by using that kind of hyperplane section argument. On some other argument I will describe later in the case of the argument in SGA2. And actually, so this argument of Grauert and Spencer, so I've directly influenced the proof of by Serre of the Gaga theorem, but it's also an argument that plays a key role in the solution by Grauert of the Lévy problem. So that's maybe a small aside to the main topic of this lecture, but I would like to explain how that kind of argument also occurs in Grauert's proof. Duration. It's basically at the same time, maybe in 58, something like that. So the Lévy problem is assertion that, well, solving the Lévy problem amounts to prove that some kind of pseudo-convexity property, let's say of some complex manifold, of some complex domain in a complex manifold, and so on, implies, let's say, the existence of many analytic functions, or something like that, some property of holomorphic convexity. So for instance, assume you are given some nice pseudo-convex domain. So it's difficult to so this is a picture of a pseudo-convex domain in some analytic manifold. So you have given M, let's say, a nice domain with infinity boundary, relatively compact in some analytic manifold. So you make some pseudo-convexity assumption on the boundary. So concretely, it means that if you look locally at M near at some point at the boundary, it's isomorphic to some convex domain, let's say with infinity strictly convex domain in the usual sense, in the naive sense, into Cn. Okay. The point of Grauert's solution, one of the points of this paper, but maybe the key point of this paper, is to prove that in that kind of domain, if you have given, let's say, you have a lot of holomorphic functions. This is holomorphically convex, for instance. And the proof of Grauert goes as follows. So a first thing that is quite easy to see is that in this context, of course, you can slightly enlarge M. You may put M in some family of domains, M epsilon. So M is M0. And you may have some M epsilon, and epsilon is larger, small epsilon, by moving by small epsilon the boundary. So this is M.
Sorry, do you assume they are strongly?
Yes, strongly. Strongly, yes. Okay, strongly with all the smoothness assumption you want. So this is M, and you can put M, you can slightly enlarge it if you want, M epsilon. So the proof goes as follows. First, he proves that for any, let's say, coherent sheaf, F, let's say, maybe on the ambient manifold with one M plus, for instance. So H1 is finite dimensional. And the argument for this, okay, in Serre's proof, you need to have a finiteness assumption on H1, as in Coder and Spencer, but for any coherent sheaf. And this was proved by Cartan and Serre by some very nice compactness argument. And this compactness argument may be used to prove that this map is on, well, which is on 2 for M epsilon on compact. And this implies this finiteness. So this is an argument à la Cartan Serre you get by telling that you can go from M to M epsilon by adding some kind of balls successively. And then, once you have done that, of course, this will work for M, also for M epsilon. Once you have done that, you can apply the same trick. For instance, if you take a point here on the boundary, so point P, you may choose, so locally, your point is a point at the boundary of a strongly convex domain in Cn. So you can take some hyperplane that touch the boundary of this convex domain exactly at this point. So you can, here, you're working locally, you can find, let's say, an hypersurface H here, H, an analytic hypersurface that will be contained in m epsilon minus m, and that touch the closure of M exactly at the given point P. And moreover, okay, this analytic hypersurface can be, let's say, it can be bialomorphic to some convex domain in Cn minus 1. So you know that you have no H1 for any, let's say, current sheaf or trivial, or for the structure sheaf on this analytic hypersurface. And you also know that you have a lot of holomorphic function on H. And now you can apply the previous argument with x equals m with L equals O of dH. Well, no, you should not say things like that. You may replace O of 1 by O of H in the previous argument. And you see, you still have the vanishing H1. You have the H0 is very large. You still have the finiteness of these groups. So at the end, you get that still the surjectivity for n large enough of global section over M over M epsilon. Global section of O of NH that is holomorphic, well, meromorphic functions on M epsilon that have only a poles with order at most n along H to the possible residues for the of higher order of this meromorphic function of H. So at the end, you get you see that you can find some holomorphic function on M epsilon. Well, a meromorphic function on M epsilon that is holomorphic everywhere outside along this surface on that pole of order n there. So it gives you some holomorphic functions on M that goes to infinity at this point. And it proves the holomorphic convexity. So it's basically the same trick that occurs in Grauer's proof. And actually it seems that Siegel did not like this argument at all. Grauert explains that Siegel was very puzzled by the deep ineffectivity that in the argument of Grauert, and the ineffectivity occurs exactly at this point. Well, anyway, Siegel seems to have been not such a nice man, so he doesn't prove anything seriously. But anyway. Okay. So this is the end of the digression. And now I would like to discuss properly the content of SGA2. So here is a baby version of the main result of SGA2. So it's a result theorem that is due to Grauert and Grothendieck. Apparently, SGA2, the content of GA2 was motivated by some preprint of Grauert. It's explained by Grothendieck in the introduction of the seminar, but I have not been able to find any trace of this preprint. I asked to some people like Michel Reynaud who had been there. I also asked once Peternel, but apparently, okay, it's somewhere. So let's consider X, let's say in Pn of C. Some smooth on projective of dimension d. And let y an hyperplane section, if you want. Or more generally, any ample divisor will do. So ample hyperplane section. So there are two parts in this theorem. The first part, that is apparently was in the manuscript of Grauert, is some kind of comparison theorem, but only for H0. It asserts that if the dimension is at least 2, then for any vector bundle, let's say analytic or algebraic, but it's the same now, a vector bundle, E over X, the map from the global section of E over X to the germs of analytic sections. Of E along Y. This map is an isomorphism. And in SGA2, this type of property is called Lefschetz property, and the abbreviation is Lef. And the second part of the theorem is an existence theorem. Grothendieck. It asserts that if the dimension is at least 3, if D, then any germ of analytic vector bundle along Y may be extends to some current analytic sheaf, let's say current analytic or algebraic sheaf on X. So this extension possibly may not be locally free everywhere, but it's the set of points where it is locally free is open and contains a hyperplane section. So it's the complement of a finite set of points. So it's necessarily locally free on X minus F, where F is a finite subset in X minus Y. And in the case of line bundle, of course, you may take F is to be empty by smoothness. And in SGA2, this kind of property is called Lefschetz effective, and it's written Lef with 2 Fs. So it's not the most efficient notation to use when you discuss this matter, but okay, it's like that. So you may think of these two parts really as counterparts of the two parts in Gaga theorem of Serre. Okay, now I would like to formulate a series of comments. So of course, in SJ2, Grothendieck works in a framework of not on analytic geometry, but of formal geometry. So I'll replace analytic by formal. You replace C by any Noetherian base scheme. You replace X by some scheme X over S on Y. So X is X will be projective, relatively projective, and while I will be a relative Cartier divisor. Relatively ample. And moreover, what is quite important is that D is a relative dimension in this case. So with the chain of notation, what I said still holds basically, provided everything is still smooth, but actually you can reconcile, you see the smoothness assumption by working with conditions on the depth, so on use depth. Conditions instead of dimension conditions. Okay. Okay, this is so not to cheat too much. Maybe this I would like to keep. So, of course, the difference between these theorems in SJ2 and a theorem like Gaga's theorem is that here you have assumptions on the dimensions. And it's, of course, these conditions are quite important. For instance, in dimension 1, Grauert is certainly wrong. Think simply of a point. Y is a point in X, which is P1. If you have a formal germ of an analytic germ at a point, it doesn't extend to always to regular functions everywhere. It's clear? For instance, in dimension 2, Grothendieck is not true. And it's maybe more funny. For instance, it doesn't hold for P1 inside P2. For instance, so let me draw a picture. So it takes a line in the plane, so coordinate X, coordinate Y, and take any formal, any germ of analytic functions in the variable y, and you consider its graph. Here, the transverse germ of transverse curve defined by x equals f of y. So this is P1, and here you are in P2. And here, you may prove as a consequence of Grauert, it's an exercise, that the line bundle defined by the germ of line bundle along P1, defined by this divisor, O of t, is algebrizable if only if f is if of the very simple form, f is a polynomial of degree at most 1. So you see, it's very easy to construct line bundle, algebrizable, well, non-algebrizable line bundles. Okay. But of course, these theorems have a lot of very nice geometric consequences. One, two, three. For instance, sorry? Oh, it's okay. It's you are in the affine plane. You compactify by P2. Okay. For instance, if you work with the trivial line bundle, you see that this implies that Grauert implies that if X is connected, then Y is connected. Well, if Y is not connected, you can find a function on Y that is analytic or continuous and takes the value 0 on 1, that takes effectively 0 on 1, and you extend it by continuity as a locally constant function near as a germ. But if it has to come from a global function, and if X is connected, it doesn't exist. So, for instance, the simplest case of this maybe is when X is P2, and you recover this whole theorem of Puiseux that was what was on the starting point of our story. Okay. For instance, another thing you get that, for instance, a very concrete consequence of Grothendieck for instance, you get that a germ, so you D at least 3, a germ of analytic hypersurface in X along Y extends to is a germ of some analytic of some algebraic hypersurface in X. Because, okay, you prove this as follows. You have this germ. Let's call it H. You look at O of H. It is a germ of an analytic line bundle. It extends to a global line bundle. But it is not. Of course, you have the tautological section of this analytic line bundle, the divisor of which is your germ, extends by Grauert to a global section. So it means that actually you are considering a global hypersurface on this germ. Okay? On this, for instance, already for P2 in P3 is not something completely clear. Okay. So in SJ2, these theorems are used to compare the fundamental group or the Picard group algebraic fundamental groups.
Sorry, but why you say that this implies fusel? Fusel was about finding cars minus a certain number of points.
Yes, maybe I'm cheating a little bit. But once you know very little about analytic curve, you know that, well, maybe, yes, maybe it's not completely correct. Well, you need to work on the normalization. Well, yes, if you know a little bit of Italian geometry, that you can resolve the singularity of curve, you can do it. Okay. Wow, it's not very clear. So the idea in SGA2, you want to compare invariance of y on x in the style of the whole Lefschetz theorem. The idea is to use, let's say, the germs of the germ of x along y as some kind of go-between. For instance, let me explain how to use these theorems to compare algebraic fundamental groups. So theorem. Oh, it's a corollary. So you suppose that X is connected, and you take a base point in, let's say, choose it in Y, and I claim that Gr1, Gr2 implies that when D is at least 2, Y is connected. But, okay, it's already said. And the pi 1, algebraic pi 1, maps onto the algebraic pi 1 of X. And I claim that when D is 3, this map is an ISO. So the proof works as follows. The point of Grothendieck approach for comparing fundamental groups, let's say algebraic fundamental groups, is his own description in SGA1 of algebraic fundamental groups in terms of finite étale coverings. So you have, if you have Y, let's say in X, both connected for simplicity. So you have a map between algebraic fundamental group and the property of these maps precisely express the properties of the functor, which from the finite, the category of finite étale covering of X, you have this the functor from the finite étale coverings of Y. And the functor that is simply the restriction, base change to I, restriction over to I. So you send this to x tilde over y, and nu is nu over. If you have a finite étal covering of x, you get by restriction to y a finite étal covering of y. Okay, so you get a set with a lot of structures there, and the sets are the category of these coverings are classified by these profinite groups, and these maps here translate the property of this functor. For instance, the surjectivity of this map corresponds exactly to the fact that for any such things, its restriction to y is always connected. And of course, the map is a bijection if only if this functor there is an equivalence of category. The right column is what you get when you unwind the definition of what is the left column. Okay. Okay. Now, for instance, let us prove of one. Okay. The point is that if y is an ample divisor in X, for any finite covering, its pullback is still ample. Here we don't even use the fact that it is étal. Okay. New finite. Y ample. No. Oh yes. This is a fancy way to write a new inverse of y. Divisor in X this implies that Mr. Y is an ample divisor on X tilde. And here, of course, X tilde has dimension at least 2, and if you plug rho 1 to, well, the connectedness part that I already explained, you get that this inverse image is connected. Okay, and now the proof of 2 really use the full strength of Grothendieck 2. The point is that, okay, what you need to show is that you are given some finite étal covering of the ample divisor y. You can extend it to finite étal covering of the wall over the wall of X. And you translate this question to a question about extending coherent sheaf of algebras. So the idea is to go in two parts. It's basically clear that a finite étal covering of y, so y tilde, extends for trivially to a germ of finite étal analytic covering of some analytic neighborhood of y in X. This is straightforward. And now, this germ, you may encode, oh, I suppose I have to erase this. You may encode this germ so what you do, you have like this. So this, you have some open germs here, analytic open. Here you have some U tilde. So this is new, let's call this new again. And this new tilde, this covering U tilde is described by, you may look at the direct image of the analytic function of U tilde. So it's clearly a locally free, even a flat vector bundle over U. It has a natural structure of OUN algebra, and it's ununified. Here we are over C. I gave a statement over C. Well, of course, everything holds in the over any base, as I explained in the suitable formal category. But okay, I prefer to give that kind of argument in the complex setting. In a sense, the general definition of étale morphism is precisely devised to make this kind of argument to work for free in the algebraic situation. But of course, maybe if one is not familiar with this, it can be misleading, so I prefer to stick to the complex case. So, on this, you may algebraize, you may extend to something over. You may extend this locally free vector, this vector bundle, to some coherent sheaf that is locally free outside a finite number of points. And you may also extend the algebra structure by using Grauert, because you can encode an algebra structure between some product into the thing itself. And it will, so the algebra structure also algebraize. And at the end, you see that in this way, you get a finite cover. So at the end, it will extend to some x tilde 0 over the complement of finite set of points. But if you have a finite étale cover of the complement of finite set of points in a surface, that has dimension at least 2, it extends to x by purity. So you have an easy purity argument. Okay. So you see, in this way, you see that any finite étale cover of y extends to finite étale cover of x. Of course, it's unique, as the previous part. And it gives you exactly that this map is an isomorphism. So you can play similar games with with speaker group. Maybe you have to add something. Maybe I will not discuss this. Okay. Now, of course, now I would like to discuss in somewhat more details the formal case, the formal version of this. So I need to recall you a few basic facts. I will need only a very little bit of formal geometry. So let me try to be specific. So if you start with some Noetherian scheme, on Y, some closed subscheme, is defined by some ideal sheaf, Iy. You may consider the successive thickenings defined by the power. And you may define the formal completion of X along Y. It's a ringed space in I should say topologically a ringed space. So the underlying space is the same as the underlying space of Y. And for any U open in XY, so an open subset R, or the sheaf of regular function, let's say, formal function of U is the limit, projective limit of the section of O of Yn over U. And this is equipped with a pro-discrete topology. So it's quite easy to define completely what a formal completion is. It's slightly more tricky to introduce a suitable category of abstract formal schemes because you need to have the static conditions and so on. But here we don't need it. So it turns out that this sheaf of rings satisfies some current conditions, so it's fair to consider current sheaves of that kind of current sheaf of this formal completion. But actually, current sheaves of the formal completion are exactly given by compatible systems of current sheaves on the schemes Yns. Current sheaves. Systems. So it should be something like this. It's the same thing as a system like this. En, some data. So En is current on Yn. And you have an additional piece of data. You are given an isomorphism between the restriction of En plus 1 to En with En. So you have some So the natural operations, the tensor operations there corresponds to the similar operation stepwise. Okay. So in a sense, you could work with some kind of pro-category of current sheaf on these things, and it will be equivalent. And also, by the very the section of a current sheaf on the formal completion is a projective limit of the section of the sheafs. Current sheaf is defined on the successive thickenings. No, well, it's, I suppose. I hope I have not.
Yeah, clearly these isomorphs may be abstract.
Yes, well, it's the same thing as given the abstract isomorphism. I can suppose the isomorphism to be part of the data. I suppose it's correct. Maybe I'm wrong.
I think that you need that you have an exact sequence en minus en plus 1 to en, and the kernel is exactly given by the ideal.
Yes. Grumpf. Well, at least it's true for locally free sheaf. I have to think. Okay. Okay. So an example of a way to get a current sheaf on the completion is if you start from some current sheaf on the global space. So E, example. For instance, E, if you start from E current on X, you may associate, say, its restriction to xy, to the completion, and it will be the system defined by the restriction of E to the successive neighborhood equipped with the obvious isomorphism corresponding associated to the restriction map. Plus, I don't write them. And now, the current sheaf on x bar y on the completion that may be defined by this construction by E current on x or on some Zariski neighborhood of y in x are the algebrizable current sheaf. And now, with this, using this language, you may phrase a purely algebraic version of the theorems of Grauert and Grothendieck, and that's the one that actually occurs in SJ2. So for instance, we work over some base field K. So we start with X, smooth projective scheme over some field K, and you take Y an ample effective divisor on X, and then you have Grau1 and Grau2 that you get by simply changing the notation. If D, the dimension of X is at least 2 for any vector bundle, for any locally free sheaf, for any vector bundle E over X, the map from the actual regular sections to the formal sections along the completion is an isomorphism. So here I have replaced germs of analytic sections by formal sections, so it corresponds to sections on compatible systems of sections on the successive sequenings yn of y in x, and you have Grothendieck if d is at least 3, any vector bundle E hat over x at y is algebrizable. So here it means, as I explained before, a vector bundle over the completion is nothing but a sequence of a compatible sequence of vector bundles on the successive sequenings. Okay. And now it's a fact that, for instance, this corollary on its proof extends without basically any change to this general setting by the same proof. This corollary extends. Corollary on P1 still holds absolutely without any change. And the proof is the same up to some details. Here you have, for instance, the connectedness argument for the first part of the proof is the same one. And here, to extend to, we had to work with sequenings. We had to construct some covering of x starting from a covering of y. And here we used some kind of intermediate covering of a small neighborhood u in the analytic topology of y. But in the formal situation, the proof, these constructions becomes basically empty. It's basically the definition. Well, let me explain that. Only change in the proof of 2. So you start and actually the very definition of a finite étale covering means that if you take a sequening to y1, for instance, it extends to something finite on étale. It's a definition of a étale morphism by the fact that you have a unique lift when you have an extension with a sheaf of square 0. But if you have done it once, you can do it twice. And so on. And in actually, you get some kind of thickening of this. You describe at the level of algebra just as before, and you go from there to x again by using go2, and from x minus f to x again by using some purity argument. Actually, the purity argument here is slightly less sophisticated in general, in higher dimensional case. It's a Zariski-Nagata purity, so it is not completely elementary. But basically here it's a definition of étal morphisms. Okay. Algebraic definition. So you see, in this way, you prove you get a pure algebraic proof, modulo you have a proof of Grauert and Grothendieck, of this, let's say, Picard, Castelnuovo, Enriquez, Lefschetz theorem. Okay, it's a good point to stop. Thank you. Sorry?